Hello students, today we are going to start chapter number 2, electrostatic potential and capacitance. Students, we have already studied the potential and the potential energy related to the earth in the chapter of gravitation. So here also many things are similar. Here we are going to study about the potential energy due to static charge particles. Static means stationary. Also, we will study about the capacitance. Now, what is this capacitance? So, capacitance is the capacity of a component to store electric energy. Now, the name of this component is capacitor. In 10th standard, you have studied about resistor and its resistance. So similarly, here there will be a capacitor which has its capacitance. Now, where this component capacitor used in a circuits? These capacitors are used in most of the electric components or the gadgets. You can see here there is a CFL bulb. Its interior part is shown here. You can see this green color is a capacitor used here. Even this blue color component is also a capacitor. So this type of capacitors are used in CFL or LED bulbs, and this type of capacitors they are used in various electric motors. Even we know that fan also rotates due to electric motor. So you will find this type of capacitor in the fan also. Students, you can see a circuit here. In this circuit, this component which has a color bands in it, these are resistors. You will study about resistor in next chapter, chapter number 3. Even this is also a resistor. This component is also a resistor. Then the components which you see here, black color having silver band on it, these are diodes. Even this is a diode. Diode is a semiconductor device. Even you will study about this semiconductor devices also. Now here this blue color component and this red color component, they are capacitors. So we can say that this type of components are mostly used in the circuits. I had given you the example about the use of this capacitor in fan, in CFL or LED bulb, but these are used in most of the gadgets, in computers, in mobile circuits, etc. These components of the circuit has their individual specific functions. But here we are going to study about the functions of the capacitor. Now, the main function of this capacitor is to store the electric potential energy. So now let us first understand the word electric potential energy related to the static charge particles. Now here in this topic 2.1, which is nothing but it is an introduction part. Now students, gravitational force, force in a compressed or a stretched spring, as well as Coulombian force, which is nothing but it is an electrostatic force. These all forces are the conservative forces. Now in this type of conservative forces, when a particle is moved from one point to another, then the external force is required, and this external force is always against this type of conservative forces. And so in such process the work is done, and due to this work done the energy gets stored in the form of potential energy. As an example, we know that if we want to stretch a spring, then we have to apply the external force. Here we can say if this is a spring in its original condition, so I have to apply an external force to change the configuration or a length of a spring. And when this external force is applied, I need to do some work, and so this work gets converted in the form of elastic potential energy of a spring in this case. Here we must note that when the external force is applied, inside the spring also a restoring force is produced. Students, you have already studied about the conservative forces, but still once again I'll explain you what are these conservative forces. One important thing about these conservative forces is that the work done in such type of forces does not depend on path. Suppose if we take 2 points P and Q in a space where the conservative forces are present. So if we move any particle from point P to Q, there are many paths to move that particle from one point to other. We can move zigzag, we can move straight, we can move in a curved path. So there are many paths, but the work done here will not depend on the path. It only depends on the initial position and the final position. So this is an important thing about the work done in a conservative force. One more thing is, in such type of conservative forces, the potential energy and the kinetic energy, they may convert from one another, but the energy loss in other form is zero. Ideally the energy loss in such type of case is zero. We have studied in simple harmonic motion that when an object is suspended with a spring and if it is pulled downward and then released, it will start its oscillations. So when it moves up and down, potential energy and kinetic energy they gets interconverted. But here the condition is not ideal, and so we know that the damping takes place due to the conversion of some of the energy in the form of heat due to friction with the air. But if the ideal condition is considered, then we can say that in a spring, potential energy and the kinetic energy will go on interconversion, and at any time the mechanical energy will remain constant. And so this is all about the conservative forces. Now students, one more question will arise in your mind, that if the gravitational force, electrostatic force and the force in a spring are conservative forces, then which are the non-conservative forces? I'll give you one example. If I'll move a block from one point P to other point Q, in that case we know that as the block moves there will be friction with the surface, and due to this friction some of the energy which is used gets converted into heat, and so we can say that the frictional force is a non-conservative force. Now let us see an important theory related to the work done by the external force against the electrostatic repulsive force, and this work done gets stored in the form of electric potential energy. Now in this theory we have to consider a charged particle kept at the origin. Here this charge is symbolically taken as capital Q. Now a small charge which is called a test charge is brought from point R to point P. So here when this small charge particle Q is brought from this point R to P, the work is done against the electric field of this charge, and so that work done gets stored in the form of electric potential energy. Once again, understand this figure. Here a positive charge Q is kept stationary, fixed at its position. Due to this charge particle there is an electric field which is shown by this, and we have taken a test charge Q at point R initially, and then it is moved along this radial path towards point P. So it covers in all this much distance. Electric field is in this direction and the displacement is opposite to it. and so we can say that the work is done against the electric field. So here this charge Q is moved due to this external force. Already the electric force is acting on it, and due to this external force, which is equal in magnitude but opposite in direction, and that's why there is a negative sign here, because these two forces, they are equal in magnitude and opposite in direction. So definitely in such cases the resultant force or the net force will become 0, and if the force is 0 then the acceleration is also 0, and if the acceleration is 0 then this charged particle must be moving with the constant speed along this path. So here we need to keep the speed constant, and so the electric force which is acting in this direction and the external force is applied in this direction, which is having the same magnitude of this electric force. Now we will consider a intermediate condition with a very small displacement dr. Actually the particle is brought from point R to point P, but we need to consider a small displacement, and we'll calculate the work done for this small displacement, and then for this entire displacement from R to P we will integrate. So here also work done to bring a charged particle from point R to point P due to external force is given by WRP in the form of integration. Initially it was at R, so this is initial limit of integration. Finally it is reaching at point P, so this is final position, and we know that the formula for the work is force into displacement, and it is a dot product of two vectors. Now from equation number 1, F external is equal to minus F electric force. So here replacing this F external by Fe and taking negative sign outside, we get this next step. Now this work done is against the electrostatic repulsive force, as I said earlier, and this work done gets stored in the form of potential energy. Now this potential energy is the difference of the potential energies at point P and at point R. This means that when the charged particle is kept at this point, at that time also it has a potential energy with respect to this point R, and when it is brought at point P, so even at this point also the charged particle has the potential energy with respect to point P, and so when we move the charged particle from here to here, there will be a difference of the potential energy which is obtained due to work done. Now you can understand the definition of this electrostatic potential energy. Next part is about some important points related to this theory. Here, first point says that the work done by the electrostatic field in moving a charge from one point to another depends only on the initial and the final points, and it is independent of the path taken. This means that when the charged particle is brought from its initial position to final position, the path is not important. You can see here we can choose various path and can reach from R to P. We can move in a straight path or in a curved path or in a zigzag path. But this work done and so the potential energy does not depend on the path. It only depends on the initial position and the final position. Now point 2 says that the definition of electric potential energy difference is obtained from the physically meaningful quantity work, because initially we started from work and then we reached to the potential energy difference. Now about this third point, we have obtained the equation of work done from R to P, and that is obtained as UP minus UR. This was the equation we obtained for the potential energy difference. Now here it is given that if this point R is taken to infinity, we can see here this is infinity, then in place of R we can write infinity. So in this case, when a charged particle is brought from infinity to a given point P, we get the potential energy of point P. It is because when we write infinity in place of R, potential energy of infinity is always 0. And so if we put infinity is equal to 0 here, then we will simply get the work done as UP only. Hence, we can define the potential energy of a charge Q at any point as the work done by the external force in bringing a charge Q from infinity to that point or a given point. So I hope students you understand this topic very well. If you have any doubt, then you can ask me.